Welcome to the Creative Commons RX podcast. Before diving into this episode, I want to ensure we're all on the same page. This is for general informational purposes only and does not constitute the practice of medicine, nursing, or other professional healthcare services, including the giving of medical advice. No doctor-patient or pharmacist-patient relationship is formed. Using this information and the materials linked to this podcast is at the user's risk. The content on this podcast is not intended to substitute for professional medical advice, diagnosis, or treatment. Users should not disregard or delay in obtaining medical advice from any medical condition they have, and they should seek the assistance of their healthcare professionals for any such conditions. Clinical experts created the references, content, and clinical insight. NotebookLM, a Google AI tool, created the audio content, which I extensively reviewed before release. Finally, the host states that he takes all conflicts of interest seriously. Currently, there are no conflicts to disclose. For all of his disclosures and the companies he invests in or advises, he directs users to reach out independently, where he keeps an up-to-date and active list of all disclosures.
Welcome to The Deep Dive. We're the show that digs through the sources to give you, well, the real story, a shortcut to being genuinely informed.
That's the goal.
And today, we're tackling something you almost certainly have at home, acetaminophen. You know, Tylenol, paracetamol, it's everywhere.
Absolutely. Millions, probably billions of medicine cabinets worldwide. Your go-to for a headache, fever.
Right, the everyday stuff. Seems totally harmless, doesn't it? Almost boringly safe.
That's the perception. But beneath that surface, there's some really complex pharmacology and, importantly, a real potential for danger if it's not used correctly.
That's what we're diving into today, acetaminophen toxicology. It sounds heavy, but it's fascinating.
It really is. We're going to trace its, well, pretty surprising history, how it went from being ignored to being everywhere.
And we'll get into the nitty-gritty, how your body actually processes it, those metabolic pathways.
And crucially, what flips the switch? What makes this common drug toxic?
Plus, how doctors diagnose an overdose, and critically, how they fight back with treatments.
Our mission today is really to give you that deep understanding, cut through the noise.
Yeah, expect some aha moments. We're going to hit some surprising facts, some critical insights that might honestly change how you view this medication.
You'll get why it works, but also grasp that pretty narrow safety margin it has.
And the science behind treating an overdose, it's genuinely life-saving stuff. Knowledge that could really matter. So let's get started. Let's unpack acetaminophen. Okay, so let's start at the beginning, because the origin story is, well, not what you'd expect for such a common drug.
Not at all.
It was first made back in Germany, 1887, a long time ago.
That's right, but it wasn't an overnight success. Far from it.
No, it's basically put on the shelf. Why? Concerns about toxicity.
Exactly. The medical world back then was worried it might be harmful. They actually preferred other related drugs, things like phenacetin and acetanilide.
Which sounds counterintuitive now because those drugs had issues, didn't they?
Big issues. A major side effect was something called methemoglobinemia.
Right, I've heard of that. It affects how your blood carries oxygen.
Precisely. It messes with the iron in your hemoglobin, so your red blood cells can't bind and deliver oxygen effectively. That's a serious problem. So while those older drugs worked for pain and fever, they came with this significant risk.
Okay, so here's the twist, the aha moment. Researchers eventually figured out something pretty crucial.
They did. They discovered that N-acetyl-P-aminophenol, that's APP, or paracetamol, was actually the main active metabolite doing the work in those older drugs.
So it was the key ingredient hidden inside the problematic one.
Basically, yes. And the really key part, AP did the job, pain relief, fever reduction, but with a much lower risk of causing that methemoglobinemia.
Wow, so the safer alternative was there all along, just unrecognized.
It was the first real glimpse of its potential. A safer derivative, ironically, from the very drugs that overshadowed it.
But even with that discovery, it still took a while for it to catch on, didn't it?
It really did. Acceptance was slow. APP was only introduced clinically in the US and UK around the mid-1950s. You know, Tylenol, Panadol.
Mid-50s, but it didn't really explode in popularity until the 70s.
That's right. Decades later, those early concerns about toxicity, that shadow from phenacetin and the others, they lingered. The medical community was just very cautious, understandably so, given the history.
But once the research firmed up, proving its safety at the right doses,
then it took off. Popularity absolutely soared.
and you saw this explosion of different products, single ingredient combination meds for cold and flu.
Oh yeah, it's in everything now. And different ways to take it, tablets, liquids, even IV forms in hospitals. It became a standard fixture.
But that very ubiquity, especially being over the counter, leads straight to the problem we face today, doesn't it?
It's the great irony. That easy access is a major factor in why it's so frequently misused in overdoses.
Making it a leading cause of acute liver failure.
In many places, yes, a leading cause. The very convenience that made it popular is now its most dangerous feature. It shows how even a seemingly safe drug has a dark side if you cross that dosing line.
And what's really striking, you said it became popular in the 70s, but the toxicity from overdose wasn't even formally recognized until 1966.
Yeah, as late as 66. The first reported cases were out of Scotland about 10 years after it hit the market.
Just imagine, people were overdosing, getting seriously ill, potentially dying, and doctors might not have even connected it directly to the acetaminophen.
It really underscores how much we've learned. Back then, the struggle was immense because there were basically no effective treatments for an overdose.
So as overdoses increased with its popularity, so did severe illness and deaths.
It was a really worrying trend, and that dire situation is what really pushed the research forward to find an antidote.
Which brings us to Dr. Laurie Prescott and her team in Edinburgh in the 70s. They were pioneers here.
Absolutely pivotal work. Their key contribution was making that direct link. The amount of APAP in the blood predicts the risk of liver damage.
They quantified the risk.
Exactly. And their animal studies were crucial for understanding how APAP worked, its mechanism, and importantly, testing potential antidotes.
Which led to trials looking at things like cysteamine, methionine.
And eventually, N-acetylcysteine.
The winner.
By the late 70s, the UK studies cemented NAC as the antidote of choice. A massive breakthrough. Finally, an effective treatment.
But even with NAC, the death rate didn't drop as much as expected.
Surprisingly, no, which tells you something about the scale of the problem. It prompted the UK to take public health action in 1998.
Restricting pack sizes for over-the-counter sales.
Yes, a direct attempt to reduce fatalities. It highlights the ongoing challenge. This drug is just so deeply embedded in society.
And we still face challenges today, right? Accidental overdoses.
Definitely. People taking multiple products without realizing they all contain APAC, confusion over labeling.
Different strengths, different formulations like modified release.
Or the IV forms used in hospitals, they all add layers of complexity to managing overdose situations. It's a constant effort to stay ahead.
Okay, so to really get why APAP can be dangerous, we need to look inside the body, specifically the liver. That's where most of the action happens.
The main processing plant for APAP.
Exactly. And it uses 3 main pathways to metabolize it. Now, at normal therapeutic doses, most of the drug goes down the first 2 pathways. We call these the safe pathways.
Okay, so what are these safe routes doing?
Well, the primary one is called glucuronidation. It handles over half, more than 50% of the APAP clearance.
Glucuronidation, what does that involve?
The liver basically tags the APAP molecule with something called glucuronic acid. It's a large, water-loving molecule.
Makes it water-soluble.
Precisely. So your kidneys can easily grab it and excrete it in urine. Nice and clean.
Okay, that's pathway 1. What's the second safe one?
That's sulfation. Handles about 40% of the metabolism. Similar idea, the liver adds a sulfate group this time. Again, making it water-soluble for easy removal.
Exactly. So you see, at normal doses, the vast majority, like 90+%, gets processed safely through these 2 routes. Non-toxic byproducts, easily removed, it's efficient.
Sounds very neat and tidy. But there's always a but.
There is, because a small fraction, only about 4% at normal doses, goes down a third, very different pathway.
The dangerous one.
The dangerous one. It's called cytochrome P450 oxidation.
And what's different about this pathway? Why is it dangerous?
Unlike the other 2, this one doesn't make a harmless, easily excreted product. Instead, this P450 pathway, mainly using an enzyme called CYP2E1, leads directly to the formation of something called N-acetylpipbenzoquinonamine.
Okay, that's a mouthful. Let's call it NAPQI.
NAPQI, good idea. And NAPQI is the bad guy here. It's highly reactive, highly toxic. It's the molecule responsible for APP poisoning.
So even at normal doses, we're making a tiny bit of this toxic NAPQI all the time.
We are. But crucially, our bodies have a built-in defense system for that small amount.
Glutathione.
Exactly. Glutathione is a powerful natural antioxidant, a scavenger molecule. It finds that NAPQI and detoxifies it very effectively at therapeutic doses.
How does it do that?
It binds directly to the NAPQI, forming a harmless, non-toxic complex that, again, is water-soluble and easily excreted. Think of glutathione as the liver's dedicated cleanup crew for NAPQI.
Keeping things safe under normal circumstances. But the system breaks down in an overdose.
That's the critical point. When you take way too much APP, the liver produces way too much NAPQI. far more than the glutathione cleanup crew can handle.
The glutathione gets used up, depleted.
Completely overwhelmed and depleted. And when there's no glutathione left to neutralize it, the toxic NAPQI starts to build up.
And it doesn't just float around, does it?
No, it's highly reactive. It starts binding indiscriminately to vital components within the liver cells, proteins, lipids, cellular machinery,
Damaging the cells directly.
causing direct cellular injury. If enough cells are damaged, it leads to liver inflammation, necrosis cell death, and potentially acute liver failure. That's the core mechanism. Overwhelming the natural defense lets the toxin run rampant.
And this damage goes deep, right, down to the mitochondria, the cell's power plants.
Absolutely. APEP overdose causes significant mitochondrial injury. It's a key part of the liver damage process.
How central is it?
Very central. Animal studies actually show that if you can prevent that mitochondrial injury, you can significantly reduce the overall liver damage from APAP. It tells you how critical that step is.
So how does NAPQI hurt the mitochondria?
When it's not neutralized by glutathione, NAPQI binds to structures in the liver cell membranes, and that specifically includes the mitochondrial membrane.
The outer wall of the power plant.
Exactly. This binding disrupts that delicate membrane, impairs its function. The cell's energy production starts to fail.
And if the power plant fails?
The cell can't make enough energy, ATP, to survive. Research shows both APP itself and NAPQI directly inhibit mitochondrial respiration, the process of making energy using oxygen.
So the energy production just grinds to a halt.
Effectively, yes. And without energy, the cell can't maintain itself and eventually dies.
What are the immediate consequences of that mitochondrial failure for the body?
Well, when mitochondria can't use oxygen efficiently, cells desperately switch to a backup plan anaerobic metabolism, making energy without oxygen.
Which is less efficient and has byproducts.
Much less efficient, and it leads to a rapid buildup of lactic acid. This causes metabolic acidosis, a dangerous state for the body.
Is that acidosis always a bad sign?
Interestingly, an early acidosis after overdose often resolves on its own. But, and this is a critical insight, if that acidosis comes back later in a patient who's getting worse, it's a very strong predictor of mortality, a major red flag.
And this whole downward spiral connects back to running out of glutathione.
It does, because depleted glutathione also makes the mitochondria more vulnerable to damage from other harmful molecules called reactive oxygen species, or ROS.
Which are like metabolic exhaust fumes.
Sort of. They're normal byproducts, but damaging in excess. Without enough glutathione protection, ROS further harm the mitochondria, creating a vicious cycle of energy failure, oxidative stress, and ultimately, cell death. It's a cascade, all kicked off by that initial overload of NAPQI overwhelming the defenses.
Okay, so we know APPAP is generally safe if you stick to the right dose. But we need to keep hammering this point. Narrow therapeutic index.
Crucial point. Small window between helpful and harmful.
And that window gets even smaller when certain factors come into play. Factors that either ramp up the production of that toxic NAPQI.
Or factors that reduce your body's ability to detoxify it, mainly by depleting glutathione.
Right. Let's talk about increasing NAPQI production first. What kinds of things do that?
We call them enzyme inducers. They rev up the activity of that specific liver enzyme, CYP2E1, the one that makes NAPQI.
Okay, examples. What should people be aware of?
Chronic alcohol consumption is a major one. Not acute drinking, we'll get to that, but long-term heavy drinking.
Okay, what else?
Certain medications, rifampicin, which is an antibiotic, isoniazid, also for TB, carbamazepine, an anti-seizure drug.
Even smoking.
Even tobacco smoking can induce that enzyme to some extent. So if someone chronically uses these substances, their system is sort of primed to make more NAPQI when they take APY.
Meaning they could have a worse outcome after an overdose.
Potentially, yes. Significantly poor outcomes have been observed.
Now the other side, decreasing detoxification, running low on glutathione. What causes that?
Again, chronic alcoholism is a big culprit here too. It depletes glutathione stores. Severe malnutrition also does that.
In a sense, the body doesn't have the building blocks.
Exactly. Other conditions too, certain muscle diseases, myopathies, and even acute starvation.
Like someone with a really bad toothache who just hasn't eaten for days.
Precisely that scenario. They might take APPI for the pain, but their defenses are already down due to not eating. That increases their risk significantly.
Okay, beyond those core mechanisms, enzyme induction and glutathione depletion, what other factors influence toxicity? You mentioned opiates earlier.
Yes, co-ingesting opiates. This is important. It can enhance APP toxicity.
How? Is it a direct interaction?
Not usually a direct metabolic one. It's more about how opiates slow down your gut. Gastrointestinal motility decreases.
So the APP just sits there longer.
Stays in the digestive system longer, leading to delayed, potentially prolonged absorption. More time for NAPQI to be formed and build up. It makes a given dose riskier.
That's a crucial interaction, especially for people managing chronic pain. What about age?
Age definitely matters, and maybe not how you'd expect. Young children often show more resistance to APP toxicity than adults.
Really? Why is that?
Couple of possible reasons. Proportionally larger liver size relative to body weight might help process it better, and interestingly, many pediatric liquid medicines contain propylene glycol.
Which does what?
It seems to temporarily inhibit that CYP2E1 enzyme, slowing down NAPQI production. Kind of an accidental protective factor.
Fascinating. And older adults?
Older individuals generally have an increased risk of liver damage from APAP. Their processing might be less efficient.
Dose and duration, obviously critical too.
Absolutely. Taking super therapeutic doses, more than recommended, even if it's spread out over a day or two, can cause liver injury. We call that repeated supertherapeutic ingestion.
And even chronic therapeutic doses.
There's some evidence, though the clinical significance is still debated, that chronic daily use, even within recommended limits, can cause slight elevations in liver enzymes in some people. Hints at low-level stress.
It really sounds like individual responses vary hugely.
Massively. Genetics play a big role. How efficiently your enzymes work, how much glutathione you naturally produce or can regenerate. It all varies.
Explains why some people seem to tolerate large chronic doses okay, while others are much more susceptible.
Exactly. And then you have the different drug formulations themselves. Modified release or extended release APAP, that poses real challenges.
Because the absorption is slow and drawn out.
Right. It messes with risk assessment using standard tools, like the nomogram we'll discuss. Requires very careful monitoring.
Okay, let's circle back to alcohol. You said chronic use increases risk by depleting glutathione, but acute use, drinking alcohol while taking APP.
Ah, yes, the ethanol nuance. This is critical and often misunderstood. Acute co-ingestion can actually be protective.
Protective how?
Because alcohol itself can temporarily inhibit that CYP2E1 enzyme. It competes with APP for metabolism by that enzyme.
So less NAPQI gets formed in that short window.
Correct. It can temporarily reduce the formation of the toxic metabolite. So the pattern of alcohol use is key. Chronic use, bad. Acute co-ingestion, potentially less bad, maybe even slightly protective in that immediate time frame. It's complex.
So putting all this together, the individual variation, the influencing factors, it makes pinning down one single toxic dose almost impossible, right?
Extremely difficult. It's less about a magic number and more about understanding the circumstances of the ingestion and the patient's individual risk factors.
So when someone comes in with a suspected acute overdose, step one is always
History, a thorough history. When did they take it? How much might they have taken? That gives us the initial risk assessment framework.
Are there any rough guidelines clinicians use, even with caveats?
There are general guidelines, but with heavy caveats. For an adult without risk factors, a single ingestion below, say, 150 milligrams per kilogram of body weight is unlikely to cause severe liver damage.
And for young kids, under 6.
The threshold is often cited as around 200 milligrams per kilogram or less for a single ingestion being unlikely to cause significant problems.
But here, these are absolutely not safe overdose levels.
Not at all. They're just general indicators.
Right.
Any suspected overdose needs medical evaluation and careful monitoring because individuals vary so much.
Okay, history first. Then the main diagnostic tool is
Measuring the acetaminophen level in their blood. Serum APP concentration, that's the cornerstone for acute overdose.
and timing is critical for that test.
Yeah, absolutely. You need to wait at least 4 hours after the ingestion before drawing the blood
Well, 4 hours.
to allow time for the drug to be fully absorbed from the gut into the bloodstream. A level drawn too early won't reflect the true peak concentration and could be falsely reassuring.
So get the level at 4 hours or later. Then what?
Then you plot that concentration value against the time since ingestion on a specific graph, the Rumack-Matthew nomogram.
The nomogram. Let's talk about that. How does plotting the point help?
The nomogram has a treatment line drawn on it. If the patient's plotted point falls above that line, they are considered at significant risk for liver damage.
And that means they need treatment with the antidote, NSC.
Immediately, yes. If the point falls below the line, the risk is generally considered low, and NSC usually isn't necessary.
Do we also check liver enzymes like AST right away?
Yes, measuring AST is recommended, especially if the patient has risk factors we discussed earlier, or if they're showing any signs or symptoms suggesting liver injury might already be starting.
Okay, let's dig into this Rumac-Matthew nomogram a bit more. It sounds like the key decision-making tool for acute single ingestions.
It is, for that specific scenario, a single acute ingestion where the time is known. It plots that serum APA concentration versus the time since ingestion.
And that treatment line you mentioned, the 150 line in the U.S.
That's right. It starts at 150 micrograms per milliliter at 4 hours post-ingestion and slopes down to about 4.7 millisig/ml at 24 hours. Above that line signifies significant risk.
How was that line originally developed? Just drawn on a graph?
No, it was based on data from actual overdose patients before NAC was widely used. It effectively separated patients who went on to develop significant liver injury, defined then as AST 1000 IUL, from those who didn't.
So it's based on observed outcomes.
Yes, though the line used today is often set slightly lower than the original line to be more cautious, to catch more potentially at-risk patients.
You mentioned the U.S. uses the 150 line. Is it different elsewhere?
It is. The UK, for instance, uses a more conservative 100 line as their treatment threshold. They treat patients whose levels fall between 100 and 150 at 4 hours, reflecting a different approach to risk tolerance.
Interesting variation. Now, for using the nomogram properly, what are the absolute must-dos?
Must use a single APAP level drawn at or after 4 hours post-ingestion. You don't plot multiple levels or try to calculate a half-life from it. It wasn't designed or validated for that.
And use the earliest possible ingestion time.
Crucial. If the patient isn't sure exactly when they took it, use the earliest plausible time. That gives you the most conservative, worst-case plot on the nomogram. Better safe than sorry.
So if the level's above the line, NAC is started ASAP, ideally within 8 hours.
Yes, within 8 hours is ideal for maximum, near 100% effectiveness. If you're waiting for the level and the 8-hour mark is approaching, or if there's any uncertainty,
Start the NAC.
start the NAC. You can always reassess or stop it later if the level comes back low and the nomogram indicates low risk. But delaying treatment past 8 hours significantly reduces its effectiveness.
Okay, the nomogram is powerful, but it's not perfect. It has blind spots, limitations. You mentioned extended release formulations.
Big limitation. The nomogram wasn't validated for those. Extended release APPA can lead to this tricky thing called nomogram crossing.
Nomogram crossing, what's that?
An initial ATP level at, say, 4 or 6 hours might plot below the treatment line, but because the drug is still being absorbed slowly from the extended release tablet, the level can actually rise later on, potentially crossing above the line at 8, 10, 12 hours or even later.
So an early all clear could be dangerously misleading.
Exactly. Requires repeated APAT levels and often a different, longer treatment approach. The nomogram also isn't validated for IV APAP overdoses, and toxicity can occur even with levels below the line in that context.
And definitely not for chronic overdoses or repeated supratherapeutic ingestions.
No, it's strictly for single acute ingestions with a known time. For those chronic or repeated overdose scenarios, relying just on AST levels might also miss early injury.
Because the damage might be slower, more insidious.
Right. The AST might not spike dramatically until significant damage has accumulated. There's also a lack of rapid, reliable biomarkers for these less clear-cut scenarios. We're still searching for better early warning tools.
What about those tricky situations? Unknown ingestion time? Pregnancy?
If the time is unknown, the general approach is, if AST is elevated or AP is detectable at all, treat with NAC. If both are normal and detectable, the risk is likely low.
And pregnancy.
Use the same nomogram, no adjustment needed. But the NAC decision involves a very careful risk-benefit discussion for both mother and fetus. 4 NAC is usually preferred to ensure the baby gets the antidote too.
And if someone presents with liver injury, but the story is unclear?
Always consider APAP, even if the level is undetectable by the time they arrive. And obviously, investigate all other potential causes of liver injury thoroughly.
Okay, moving beyond the nomogram, there's a newer predictive tool, the APAP multiplication product. Tell us about that.
Yes, this came out of the Canadian APP Overdose Study, CAOS. It's a simple calculation to predict hepatotoxicity risk.
How's it calculated?
You take the initial serum APAP level in mg/ml and multiply it by the peak serum aminotransferase AST, or ALT, in unit cell, measured within the first 24 hours of presentation.
Simple multiplication. Is there a threshold number to watch for?
A product greater than 10,000 using metric units, or if you use mg/ml in unit cell, a product greater than 1,500 indicates a high probability of significant liver toxicity.
Why is it so predictive, even in late presenters?
Because it cleverly combines two key pieces of information: the initial drug exposure, the APAP level, and the resulting degree of liver injury. the peak enzyme level. It directly links the cause and the effect.
Makes intuitive sense. What are its advantages?
Simplicity uses standard lab tests, allows for early risk assessment, and it's versatile, useful even when ingestion time is unknown, or for repeated ingestions or looking back at cases retrospectively.
Any limitations?
Yes, it's not applicable if the patient presents more than 24 hours after ingestion because you need that peak enzyme level within the first 24 hours. And crucially, like any tool, it's an adjunct to, not a replacement for, clinical judgment.
Got it. Looking ahead, are there even newer biomarkers coming? Things that might give us an even earlier warning signal.
There's definitely exciting research. The hope is for biomarkers that detect injury before liver enzymes like ALT even start to rise significantly.
Like what?
Things like microRNA 122, HMGB1, K18, GLDH. These molecules can leak out of damaged liver cells very early. They might allow intervention hours sooner.
Wow, that could make a huge difference.
Potentially, yes. They could also help stratify risk, better identifying who's really high risk versus low risk early on. Also, markers of actual liver function like blood sugar, lactate, clotting times, prothrombin time are proving better than just enzyme levels at predicting truly severe outcomes like death or needing a transplant.
Better than traditional criteria like King's College.
In some studies, yes, they seem to reflect the severity of the functional impairment more accurately.
Sounds very promising. But I assume these aren't standard practice yet.
Not yet. There are limitations. Validation is ongoing. We need more large studies to confirm cutoff values and reliability. Cost and accessibility are issues. Some tests require specialized equipment.
Like APP protein adducts or metabolomics?
Exactly. And interpreting some of this complex data, like from metabolomics, takes time and expertise, which can be a challenge in an emergency setting. So great potential, but still mostly in the research phase for now.
All right, let's really focus now on the treatment cornerstone. N-acetylcysteine, or NIC. As we've touched on, it's highly effective, especially if given promptly.
We know it works, but how does it work? What's NAC actually doing inside the liver to counteract that apotoxicity?
It works through several key mechanisms. The most important, the primary one, is all about glutathione.
Replenishing those depleted stores we talked about.
Exactly. In an overdose, NAPQI uses up all the liver's glutathione. NAC provides the essential building block, cysteine, that the liver needs to synthesize more glutathione. It directly refuels the natural defense system.
So it helps the liver help itself. It does. But NAC does more than just provide building blocks. It can also act as a direct substitute for glutathione.
How so?
NAC itself can directly bind to the toxic NAPQI, neutralizing it and forming harmless conjugates that can be easily excreted. So it's both a precursor and a direct scavenger.
A double whammy against NAPQI. Are there other ways NAC helps?
Yes. A third mechanism involves enhancing the safe sulfation pathway we discussed earlier. By providing cysteine, NAC can indirectly encourage more APAP to be metabolized via sulfation, which means less APAP goes down the dangerous P450 pathway to form NAPQI in the first place.
So it helps limit toxin production too. That's quite multifaceted.
It is. And beyond these direct detoxification roles, NAC offers broader benefits, especially in very severe cases where liver failure has already started.
Benefits beyond the liver itself.
Yes, multi-organ support. The exact mechanisms aren't fully pinned down, but it seems to improve blood flow in small vessels, microcirculation, and enhance oxygen delivery throughout the body. It might also have direct antioxidant effects beyond just dealing with NAPQI.
That sounds crucial in critical illness.
It really is. There was a key randomized trial showing that even when 4V-NAC was started, after patients had developed severe fulminant hepatic failure.
Liver failure was already established?
Yes. Even then, NAC significantly reduced the need for blood pressure support medication, vasopressors, reduced brain swelling, cerebral edema, and importantly, reduced mortality.
Wow. So it helps even late in the game.
It highlights its systemic benefits. Now, the first two mechanisms, glutathione support and direct scavenging, are most effective early, before major damage occurs. But this third mechanism shows NAC offers value even in the later, more critical stages.
Okay, so when a patient needs NAC, they can get it orally or intravenously? Are they equally effective?
In terms of outcome for acute poisoning, yes, they're considered essentially equivalent if started within that crucial first 8 hours.
So the choice depends on other factors.
Right. Things like side effects, safety profile, drug availability in the hospital, how easy it is to give to that specific patient.
Let's talk oral NAC first. Advantages, disadvantages.
Advantage? It's generally more accessible, less invasive. Disadvantage? The taste and smell. It has a very strong rotten egg sulfur odor, and it often causes nausea and vomiting.
How often?
Pretty often. Rates of vomiting are reported anywhere from 20% up to over 50%. The APP overdose itself can cause GI upset, and the NAC adds to it.
Can that be managed?
Somewhat. Giving it through a tube directly into the stomach, enteral tube, especially if the patient's airway is protected, bypasses the taste-smell issue. Antiemetic drugs can help control the vomiting too.
Okay, what about YV, NAC, pros and cons there?
Pro. Guaranteed drug delivery.
Hmm.
Essential if the patient is vomiting persistently, has altered mental status, has established liver failure, or just can't tolerate oral meds. Also preferred in pregnancy, as we mentioned, to ensure fetal delivery.
And the cons?
The main con is a higher rate of adverse reactions, specifically these anaphylactoid reactions.
Right, the non-allergic histamine release.
Yeah.
How common are those with IV?
Overall rates are around 14–18%. Most are mild flushing, itching, maybe some nausea, that's maybe 6–10%. Moderate reactions like rash or hives are also in that range. Severe reactions, bronchospasm, dangerous drop in blood pressure, swelling are rare, maybe 1%.
Is the formulation important? You mentioned older versus newer.
Yes. Older formulations not specifically designed for IV, like Mucomist, had higher reported rates, maybe up to 20%. Newer IV-specific formulations, Acetaminophen, have lower rates, perhaps around 8% overall, with only about 2% considered clinically significant reactions.
Can we reduce the risk of these reactions?
Yes. Using a more dilute solution and, importantly, slowing down the infusion rate, especially during the initial loading dose, significantly reduces the risk.
And you mentioned that fascinating inverse relationship with APAP levels.
Yes. It's consistently observed. The higher the patient's APAP level when they receive NSC, the lower their risk of having an anaphylactoid reaction.
So the APAP itself might be slightly protective against the reaction.
That's the theory that APPP might inhibit histamine release from mast cells. It's a really interesting finding that helps inform how we develop safer infusion protocols.
Are there other 5E side effects besides those reactions?
Less commonly, things like flushing, rash, chest pain, cough, headache, dizziness. Rarely more severe things like red blood cell breakdown, hemolysis, kidney problems, HUS, seizures. Also, 5E NAC requires very careful calculation, and administration medication errors are a significant concern.
Okay, so given these options, how is NEC typically dosed? Let's start with the traditional U.S. oral protocol.
Right. The 72-hour oral regimen, it starts with a big loading dose, 140 milligrams per kilogram body weight. Then it's 70 milligrams per kilogram every 4 hours for 17 more doses. Total treatment time, 72 hours, usually diluted to 5% to help with palatability. And if a dose is vomited within an hour, it needs to be repeated.
And the standard IV protocol, the 21-hour one.
That's the common 3-bag system. Bag 1 is the loading dose, 150 milligrams per kilogram, max 15G, in 200 milliliters of D5W, infused over just 1 hour.
Fast loading dose. Then bag 2.
Bag 2 is 50 milligrams per kilogram, max 5G, in 500 milliliter D5W, infused over 4 hours.
And this is where that potential calculation error comes in. It's 50 millijoule kilograms total over 4 hours, not per hour.
Critical point. Yes, the correct rate is 12.5 milligrams per hour for those 4 hours. Misinterpreting that is a common and dangerous error.
Good clarification. And bag 3?
Bag 3 is 100 milligrams per kilogram, max 10 gram, in 1,000 milliliter D5W, infused over the next 16 hours. Total time, 1 + 4 + 16 = 21 hours.
Are there adjustments for patient weight?
Yes, volumes are adjusted for smaller patients, typically under 40 kilograms, but there aren't official guidelines for patients over 100 kilograms, which can be tricky.
Now, is that 21-hour or 72-hour duration always set in stone?
Not anymore. Those were initial estimations. The modern approach, advocated by many experts, is more flexible, a variable length treatment.
Tailoring it to the patient's progress.
Exactly. You continue treatment as long as needed, based on clinical and lab markers, rather than stopping arbitrarily at 21 or 72 hours.
So when would you extend NAC treatment beyond the standard protocol?
Key indicators are, if the APP level is still detectable, say 10 millisig/ml, or if the liver enzymes, transaminases, are still actively rising at the end of the standard course. In those cases, that third 5E infusion is often continued, sometimes at the same rate, sometimes adjusted.
Some experts even base the dose on the AP level.
There's theoretical discussion about tailoring the NAC dose to the estimated AP body burden, maybe extending it for 5 half-lives of AP elimination. In practice, for very high initial AP levels, some might double the rate of the third infusion bag, though that's based more on expert opinion and experience.
What if treatment gets interrupted? Like a missed dose or disconnected 5 feet.
If the interruption is significant, maybe more than 2 or 3 hours, the safest approach is often to restart the entire protocol, including the loading dose, though some might restart from the second infusion depending on the situation.
Given the issues with the standard protocol's errors, reactions, it makes sense people look for alternatives. Tell us about those newer regimens like SNAP. Are they safer or shorter?
That's precisely the goal. Let's compare them to the standard European 4B protocol. First, the SNAP regimens, Scottish and Newcastle antiemetic pre-treatment for APAP poisoning.
SNAP.
What's different? Same total NAC dose, 300 milligilograms, but it's infused over a shorter time, 12 hours instead of 20-ish. And crucially, the initial infusion rate is lower.
Lower initial rate to reduce reactions.
Exactly. It leads to lower peak NAC levels in the blood, which significantly reduces GI side effects and, importantly, those severe anaphylactoid reactions. SNAP showed a 9% absolute risk reduction in reactions. It's widely used in the UK now.
Any downsides to SNAP?
The main initial study wasn't blinded, so there's potential for observer bias in reporting side effects, but clinically, it's been impactful.
Okay, what about the simplified 2-rate regimen?
Again, same total dose, 300 milligilograms. This one combines the first 2 steps of the European protocol into one longer infusion. 200 milligrams given over 4 hours, then it's followed by the usual 100 milligrams over 16 hours. Total time is still 20 hours.
Advantage.
Also significantly reduces infusion reactions compared to the standard fast loading dose. It's simpler, potentially fewer errors, and associated with shorter hospital stays. One study had a somewhat limited patient group, so more broad data is always good.
And the North Carolina regimen.
That uses a loading dose similar to the European one, 150 milligene kilograms, but then switches to a steady, continuous maintenance infusion of 15 milligene kilogram per hour. It's shown good safety and efficacy, including in high-risk patients.
There are also protocols that just slow down the loading dose.
Right. Extending that initial 150 milligene kilogram infusion over 4 to 9 hours instead of just 1 hour, again, aims to reduce reactions by avoiding that high initial peak NAC concentration. It might shorten the overall course, but adds complexity.
So the common theme with these alternatives is slowing down that initial infusion.
Pretty much. Slower rates, lower peak concentrations seem key to minimizing anaphylactoid reactions. Simpler protocols also aim to reduce medication errors and potentially shorten treatment duration overall. It's about making NAC safer and more user-friendly.
Which brings us back to, how do you decide when it's safe to stop NAC, especially with these variable length approaches?
It's a dynamic decision based on clear criteria showing the risk has passed and the liver is recovering. It's not just about hitting a certain number of hours.
What are the key discontinuation criteria?
First, the APAP level must be undetectable. The fuel for the fire has to be gone.
Makes sense. What about liver function, AST levels?
If the patient didn't develop liver failure, we look for the AST level to be clearly decreasing and ideally below a certain threshold, often 1,000 IUL. There should be no signs of liver failure, like encephalopathy or severe clotting problems, and again, APAP undetectable. We need to see clear improvement.
And if they did develop liver failure?
The criteria are stricter. We need to see improvement in liver function. The PTINR, clotting time, should be improving, ideally less than twice the normal value. Any encephalopathy, brain dysfunction must be resolved, and APAP still needs to be undetectable.
Plus overall clinical improvement?
Yes, the patient should be feeling better, vital signs normalizing. It's a combination of lab results and clinical picture.
And when do you definitely keep NAC going?
If AST remains persistently very high, you go 1,000. If APP levels are still detectable, or if signs of liver failure persist or worsen, you continue treatment until those resolution criteria are met.
Requires close monitoring then.
Absolutely.
Yeah.
Regular AST checks every 16-24 hours or more often. PTINR and creatinine daily if AST is up. Serial APAC levels until undetectable. Constant reassessment.
NAC is clearly the workhorse, the main antidote. But science doesn't stand still. Are there other treatments emerging, maybe working alongside NAC or offering different approaches? Fompazole keeps popping up in discussions.
Yes, fompazole is generating quite a bit of interest. It's traditionally used for toxic alcohol poisonings like methanol or antifreeze.
So how does it help with APAP?
The exciting part is its mechanism. Fompazole strongly inhibits that key liver enzyme, CYP2E1, the one that makes the toxic NAPQI in the first place.
So it works upstream from NAC. It tries to prevent the toxin from even forming.
Exactly. A standard 5e dose of fompazole, 15 milligaloki kilogram, gets levels in the blood high enough to maximally inhibit that enzyme. It's a preventative strategy, whereas NAC is more about cleanup after the toxin is formed.
What are the potential advantages of using fompazole here?
Well, many emergency docs and toxicologists are already familiar with it. It has a great safety profile. Dosing is relatively simple, no special monitoring needed for the drug itself, and its effect on CYP2E1 is predictable.
Is there evidence it works in AP overdose?
There's promising evidence. Early animal studies back in the 90s showed it worked in rats. Then case reports started emerging, a notable one in 2013 where a patient with a very severe overdose survived, potentially due to fompazole.
Any larger studies or data sets?
Analysis of the Toxis registry, a large toxicology database, found that patients who received fompazole often met criteria for needing a liver transplant, yet their mortality rate was lower than expected, around 24%. And a recent case series of 16 patients with severe APAP poisoning, including some with extremely high APAP products, reported 100% survival with fompazole added to NAC and no adverse effects noted from the fompazole.
Sounds really promising. Are there downsides or barriers?
Cost and availability can be issues. It's expensive and not stocked everywhere. And critically, while the data is encouraging, we still need larger controlled trials to really define its role, the best timing and dosing, and how it truly compares or synergizes with NAC. It's still considered an emerging adjunctive therapy.
Okay, besides new drugs, are there ways to physically remove AP faster from the body, especially in massive overdoses?
Yes, enhanced elimination techniques. These aim to speed up removal when NAC might not be enough on its own or when rapid clearance is vital.
Like dialysis.
Hemodialysis is the main one. It's very effective at clearing both AP and NAC from the blood. It's considered in cases with exceedingly high APP levels despite NAC, severe metabolic acidosis, or lactate levels that aren't improving, or sometimes before a liver transplant to clear any remaining drug.
Are there other blood cleaning techniques used?
Other specialized systems like MARS, molecular adsorbent recirculating system, or CP, single-pass albumin dialysis, can remove APP and other toxins that build up in liver failure. Their exact role and benefit compared to standard dialysis still need more study, though.
Looking even further out, what about truly experimental approaches? And let's not forget basic supportive care.
On the experimental front, things like hyperbaric oxygen therapy, breathing pure oxygen under pressure, have shown some benefit in animal studies, possibly by reducing tissue stress, but human data is lacking.
Targeting specific damage pathways.
Exactly. Research is looking into drugs that could block specific steps in the cell death cascade triggered by AP things involving mitochondria, specific signaling proteins like J and K kinases, or inflammatory molecules.
And those microRNAs you mentioned earlier.
Yes, like mirin-22. Potential there for both super early detection and maybe even therapies that modulate microRNA activity to protect the liver. Still early days for these.
But amidst all this high-tech potential, basic supportive care remains absolutely vital, doesn't it?
Absolutely critical. No matter the antidote, good supportive care is essential. This means constantly monitoring and correcting problems like low blood sugar, hypoglycemia, metabolic acidosis, electrolyte imbalances.
Managing clotting problems.
Yes, coagulopathy. Giving vitamin K helps the liver make clotting factors. Using things like fresh frozen plasma, FFP, or prothrombin complex concentrates, PCC, is guided by actual bleeding risk, not just by chasing the PTINR numbers.
And dealing with complications like brain swelling.
Managing cerebral edema if it occurs is crucial using hypertonic saline, keeping the head elevated. And as we noted, NAC itself seems to help preserve blood flow to the brain, providing another layer of support. Good fundamental critical care is key.
Wow. Okay, let's take a breath. We've covered a huge amount of ground. From the, well, frankly, surprising history of this everyday drug.
From rejection to ubiquity.
Right? To the intricate dance of how our liver metabolizes it. The safe pathways and that one dangerous route leading to NAPQI.
Understanding what tips the balance towards toxicity, the enzyme inducers, the glutathione depletion, those crucial influencing factors.
We navigated the diagnostic maze, the importance of history, the power and limitations of the Rumac-Matthew nomogram, the potential of newer tools like the APAP-T product.
And then the antidote, NAC, unpacking its multiple life-saving mechanisms, the different ways to give it, the push towards safer, more flexible regimens.
And we even glanced at the future emerging therapies like fompazole, enhanced elimination, and the non-negotiable importance of meticulous supportive care.
I think the biggest takeaway, the enduring lesson, is really the incredible impact of early recognition and getting that NAC treatment started quickly.
Coupled with that dynamic, personalized monitoring we talked about. Adjusting treatment based on the patient's response.
It's a real testament to how medical science learns, adapts, and improves treatments, even for drugs we think we know inside out.
Yeah.
And it really drives home that narrow safety window for APAP.
Absolutely. So maybe the next time you reach for that bottle of Tylenol or paracetamol, you'll have this deeper appreciation. You'll understand the complex chemistry happening inside you, the balance between benefit and risk, and the incredible science developed to manage that risk.
It's knowledge worth having.
And it leaves us with a thought to ponder. What other common everyday substances might hold similar hidden complexities, similar stories of unrecognized dangers, and the ongoing scientific quest for life-saving interventions just waiting for us to take a deeper dive? Something to think about.
This is for general informational purposes only and does not constitute the practice of medicine, nursing, or other professional healthcare services, including the giving of medical advice. No doctor-patient or pharmacist-patient relationship is formed. Using this information and the materials linked to this podcast is at the user's risk. The content on this podcast is not intended to substitute for professional medical advice, diagnosis, or treatment. Users should not disregard or delay in obtaining medical advice from any medical condition they have, and they should seek the assistance of their healthcare professionals for any such conditions. Clinical experts created the references, content, and clinical insight. NotebookLM, a Google AI tool, created the audio content, which I extensively reviewed before release. Finally, the host states that he takes all conflicts of interest seriously. Currently, there are no conflicts to disclose. For all of his disclosures and the companies he invests in or advises, he directs users to reach out independently, where he keeps an up-to-date and active list of all disclosures.